Okay, so we're going to begin to look at two proportion z procedures today, where we're comparing one proportion to another. So you guys can see this first example with graduation. So we've got two proportions we're going to be investigating here. We've got males and females. We're going to go through the exact same kind of procedure that we've done before. That's not going to change, like I told you guys. So still want to address all the same stuff pretty much. Just a few things will change for each procedure. Okay, so... Oh, I can't get to it, man. Yeah. Okay, so what do you guys think the population of interest is on this problem? What do you think? I think that's more of the variable. People who attended high school sounds good to me. Because we don't want to be including those people who didn't want to attend high school. That's actually a nice way to say that. I just said when I was in high school, I said adults. I should have at least probably said U.S. adults, right? But this is even better. So, U.S. people. I'm on the other side. Yeah. Other side. They look really similar. Hey, they look really similar. I did the same thing earlier. Okay. The variable of interest. Now, the variable of interest is what? Shh. We want to know what? Whether or not they graduated. So it's the proportion of people who graduated. Okay. What do we know? I think we know a lot of things. We know N1 or N males, you could call it whatever you like, is how many people were in our sample. Okay, we also know what else about the males. So I'm going to call males 1. If you want to say N sub M, it doesn't really matter how you write this. We also know that P hat, I'm going to call it P hat like that, okay? P hat for the males is what? 0.849%, or 84.9%, I should say. Do we have a P to compare to? No, we'll address that in a minute, but we do have some more information. Now we also know about the women. We know that there were 12, 6, 7, 8. Do you need to have the same number of samples to do comparisons? Do they even need to be this close, by the way? The answer is no. These are both fairly good size samples, though, fairly similar. And P hat, this I should have subscripted as well, shouldn't I? Shouldn't I have called it like P hat sub 1? And now this should be like P hat sub 2. Okay, so that's going to be what? 0.881? Okay. So what do we know? This should say, what do we want to know? So there's a missing thing there. It should say, what do we want to know? We want to know what? You guys tell me.
We want to know if our P hat sub 2 is greater than our P hat sub 1.
But we can say that immediately. Of course it is.
Well, if it's...
We want to know if the parameter P2 is bigger than P1. Not the sample. Well, you can see the sample right now. In other words, we want to know, are males and females different in regard to graduation? Exactly. That's what we want to know. We want to know, are the parameters for these two things actually different? Are the statistics different? Yeah, by about 4-ish%, 3.5%, right? Does that mean that their parameters are actually different? Well, it depends on a lot of factors. That's what we do statistical inference to figure out, okay? So the procedure, I think down here you can see we're not going to run a hypothesis test. I didn't have a slot for hypotheses, but we are going to evaluate a hypothesis test. We're just going to use a confidence interval to do that, like we've done in the past. You could do it all kinds of different ways. The procedure we're going to create today is a 2-sample confidence interval for proportions. Some people will call this a Z interval because we don't know any other kind of intervals yet. So I hope it's a Z interval. Okay? Assumptions. The assumptions are going to be pretty much the same as usual. I'm going to be brief about these, okay? I have 4 listed here, though. There's one extra one for this procedure. It's obvious. Okay, so what's one of the ones we should do? Randomization. But there's 2 samples, so are both samples or both groups of data randomly collected? Are they for these? Didn't they say it? They didn't. We're going to say assume each is random, proceed with caution. Okay? Second thing, my ones and my things are not lining up exactly. Sorry about that. I think you can get it though. 10%. We got to do 10%, but now we got to do it for each one. So is the population of men and women. I guess you got to do these separately, but they're so close. I just want to do them together. But is the population of men in the U.S. greater than what? 1, 2, 4, comma 6, 6, 0, 0. Duh. Same thing for the women. I think we're good, though, because they have about the same sample size, right? So then also check the women. I'm running out of space, though. Space is at a premium today. Okay, what's the other thing we need to check for this kind of procedure? I'm sorry my p hat looks so awful. I hate this dash. I'm going to go like that. Looks like fat, no. I don't care. We're going with fat. So what? 12,460 times 0.849. Is that greater than 10? Yeah, I don't think we need the specific number, but the AP exam might yell at you if you don't put it. So for them, put it. And then we also need to check being efficient today. Oh, what? Okay, I guess I'm not being efficient today. This is you suck. OneNote. See. What? Oh. Q hat. What's that going to be? Is it point? It's definitely greater than 10, but we're going to be a little specific. You're right. 1 minus 0.849, 0.151. Yes, that's definitely greater than 10. We're good. But you want to write it down. And then I'd also have to do this for what? I'd also have to do it for the women, so I got to do 4. But we're going to say also check for women. Check for the women too. And just so we're not being sexist next time, we'll check for the women and not the men. Okay? So what do you guys think is the extra assumption that we need to do if we have 2 proportions instead of just 1? We need to check not only are the samples independent within themselves, but are they independent of each other? So are samples independent of each other? So you need to think, is there any cross-pollination, basically? If that makes sense. I can't spell independent. Okay? I don't know. We don't know, so we're going to say again, assume and proceed with caution. So that's pretty iffy there. Anyway, let's do our confidence interval. That's what we really want to focus on today. So let me grab my pen. So confidence interval. I think it's going to be real similar. The theory is exactly the same. You guys have your orange sheet? Grab your orange sheet. Find the confidence interval part of it. There should be one side that talks all about hypothesis test and confidence intervals. Confidence interval is what in general? Statistic plus or minus critical value times standard deviation of that statistic. We know that already. What's our statistic this time, though? Our statistic this time should be P 1 hat minus P2 hat. All of that is our statistic. Does that make sense? So we want to see the difference between the two samples. Then we're going to have, just like it says, plus or minus critical value. What's that? I think you already know it.
It's just a 95.
Should we just do Z star 95? What is that, 1.96? This is Z star, right? We'll have T stars soon enough. And now, I want you guys to find what you think is the standard deviation for this problem on your statistics card. Here's a hint.
Oh, I'm on the wrong side. I was on the wrong side.
I think you should be able to find it pretty easily. Is this the difference of sample proportions? I think it is. It tells you exactly. There's two different things there. Do you guys see how there's two options? That's the subtle part for today. It shouldn't surprise you that you got to do PQ over N plus the other PQ over N. Because we learned last semester this is a little bit of the subtle part. Last semester when we started thinking about how to get those in the first place and we actually looked at the book's proof, it went with variance rules because variance is how spread works. We're talking about the spread in order to think about the standard deviation. Spreads always add. They always increase and they always add. Very good. So that's why you add one plus the other. That shouldn't be super surprising. I'm not going to go through the derivation with this. I think that's too much. So here we put specifically, I'll put my symbols in. I'm not going to put the numbers in. P1 hat, Q1 hat, or you could put male, right, over N1 plus P2 hat, Q2 hat, over N2. Easy peasy Japanesey. Alright, if you didn't catch that, I'm sorry. It's just too late. So now you're going to just plug these numbers, throw it all in your calculator. Do you guys really need to see that? I could do it. I guess we'll do it. Look at this. I came prepared today. Ah! This is not okay. I'm sorry. I wasn't trying to keep you awake, but I bet it did. No, oh, no, not time yet. Oh, you thing. This is scary. I'm scared. There we go. Okay, yes. There will be no cursing in this classroom. I'm just joking, mostly.
I'm saying that all the time.
Oh gosh, so scary. The moment of truth. Drum roll. Yes, that's the number I had. Okay, so a little bit of delicateness, but just make it look exactly like it does on your paper. It's no big deal. It just takes a little bit of time. There are faster ways to do this, which I will show you once we know how to do it this way. Okay, so that's just the lower bound of our confidence interval. I'll just feed you guys the other one. You could just go and put the plus there, though, right? So let's move this calculator out of the way and write down our work. So my confidence interval's lower edge is negative 0.0405. That's what I have anyway. And then when you do the plus and put that all in again, you're going to have 0.0236 or something really close to that. That's the confidence interval. Now, let's conclude. We'll first start out by doing what we practiced yesterday and just writing out real black and white, a nice simple confidence interval in context, if it'll let me do that. I don't think it wants to. Surprise, surprise. You know you want to let me do it thing. You really do. Okay, see, there we go. So we are, how confident? We picked 1.96, right? 95% confident that. Now this is the other subtle part. I don't think it's that subtle though. We are 95% confident that the true proportion of... Now, it depends how we set this up. We could have gone girls minus boys, or we could have gone boys minus girls. I think either way is appropriate. It doesn't matter which way you pick. Which way did we go? Was one boys or girls? We could go back up here, and this is why you spend some time with this stuff. It's for that reason, to help yourself. So the true proportion, yeah, you could do it either way. Here's how I phrased it: of boys who complete high school is between 4.05% and 2.36%. Now here's the key. Lower or higher? Lower. Why did I say lower and not higher? Because they were negative, right? Now if one was negative and one was positive, you'd have to put something about lower and higher, right? So that would be a little bit harder to word. Hopefully we'll do that one in a second or next week, okay? So we're going to say lower since they're both negative. Lower than what? Than the percentage of girls who complete high school. Now, that's a confidence interval. I know we never set up hypotheses on this, but as we've discussed, you can use a confidence interval to evaluate hypotheses. Remember, the question we really wanted to ask was, are males and females different in regard to graduation? How do I use this to answer that question? I don't need to start over and do a hypothesis test statistic. You've got everything you need right here. Montana. Exactly. She's got it. Did you guys hear her? Montana just said, since the confidence interval doesn't include 0, what would we do with our hypotheses? Let's just write down what our hypotheses would have been in the first place, by the way. I'll just stick them right up here. We could have written these down at the very beginning, but I didn't. H sub O, H sub A. What goes in here, parameters or statistics? Parameters. I think we called it 1, right? So we have 1. We're going to start by assuming nothing unusual is going on and that males are equal to females. Should we do a 1 or a 2-tailed test? There's nothing to suggest guys and girls are different either way, so that's probably a 2-tailed test. Oh yeah, and by the way, the thing you've got to be careful about using a confidence interval to evaluate a test is a confidence interval always has 2 tails. It's in 2 directions, right? So, what do we conclude here for our test? Oh, you can do it. You can do it, OneNote. Yay. Since the confidence interval doesn't include 0, we reject or we fail to reject? We reject H sub O or HO. Because we detected a difference. Does that make sense? They're clearly not equal. There's a difference between them. I think this should totally make sense. We reject H sub O. There is, what do you guys want to say? Strong evidence, just, or what? Those are both kind of close to 0, so I'm just going to say there is evidence to suggest that the proportion of boys graduating is different than that for girls. How much different? Well, we just specified it right there, right? at the alpha equals 0.05 level. Done. I'm going to save this just in case something happens. Okay, so let's look at another example. This time we're not going to do confidence interval, we'll just go with a straight up test, okay? So this one also says in 2000, I love the year 2000, the United Nations claimed there was a higher rate of illiteracy in Qatar for women than men. Oh, in men. Okay, so it says more men were illiterate. Okay. I would have thought the other way for the Middle East, but okay. A humanitarian organization went there. They conducted a sample. They looked at 234 men, 45 couldn't read. They looked at 251 women, 42 couldn't read. Do these results indicate that there was actually a difference? Because that's the assumption here, right? So let's test our hypotheses. Now I'm going to go through most of the process, but I'm going to abbreviate it a little bit just to focus on the important parts, okay? So you know the most of the process. Make sure you're going through it all on all of them, though. You guys can't afford to abbreviate. So, what do we know? We could write all that down. We know two proportions, though, right? Maybe we should do it, I guess. You want to do it. I'm going to do it like this time. Number of males, 234. So many buttons to remember. Number of females was 251. Fat for the males was what? You guys help me with your calculator. It's going to be 45 out of 234. What was it, Jamie? 0.192? Okay, and then p hat for the females is going to be this, which is what? That? Okay, so that's what we know. Okay, let's see what else. What's our population of interest? Definitely want to do that. What do you guys think? What? Sean, people of? Yeah, I think you're right. What's our variable of interest? I just invented a new word. You can do that in statistics. It's okay. Maybe it's a word. Crazy. I'm surprised. I don't think it's a word. Okay, whatever. Next thing we should do is probably what? Hypotheses. I didn't write hypotheses, but I think you guys got the point. Okay, so we should be putting some parameters in here. We want to say we'll assume there's nothing unusual. In other words, they're about the same. And we want to test what? They claim there's a higher rate in men, which it looks like that's what happened in our sample. You can always look here for guidance, but they specifically wanted to know if this is bigger than this. So it's a one-tail test, okay? Our assumptions, I'm just going to skip this time. Can you guys feel that? It would take a while to address our assumptions. You've got 4, though. You definitely want to think about independence between these sets, because what if they had sampled in the same family? That'd be a convenient sample, right? A lot more convenient. But what would be the problem with sampling inside the same family? They didn't tell us whether they did that or not, but you might have a stupid family. I guess that's a non-politically correct way to think about it, right? So you might have a family that's, barely above poverty level or really in the poverty level. That would be a problem, okay? So definitely address your assumptions. But I want to move on now. Let's do our test statistic. Z equals what? Statistic minus parameter. Here's where it gets a little interesting with this test. You've got to think a little bit differently. And you know what? I'm going to back this down a little bit. I need to add a couple more things here. So, if we're assuming that these guys are equal, what parameter are we going to compare to? Well, that's what's a little bit dicey. Okay? So, in the other one, we never assumed that they were equal. But here we're assuming they're equal. So, if we're assuming they're equal, and we come down here, in a second, we're going to do our test statistic, right? We're going to go like Z equals statistic. I think that's going to go the same way as before. So we're going to have like the male sample statistic minus the female sample statistic. What's the parameter going to be if they're truly equal? 0, because there's no difference between them, right? The real subtle part, though, here, which I think your stats sheet should have shown you a second ago, is what do you put in down here for the standard deviation? See, a lot of people will lose a little bit of points on the AP exam. Depending on the problem, you can lose a lot of points or just a little bit by putting in the wrong thing down here. Can we just use that same thing that we did up here a second ago? Let me scroll back up to it right here.
No.
The answer is no. Because in a confidence interval, you use your statistics to make your standard deviation. In a hypothesis test, you don't use statistics. You're trying to establish whether or not this guy is true. So what do I put down here? What you do is you pool all your data together to try to find if they were actually the same thing on a bell curve over here. Let's just draw a little drawing, okay? So here's a bell curve. If this is true and the middle is actually 0, then we want to use all this information to guess what the standard deviation of that would be. So we're going to pool it together. Okay? So that's the other, probably the subtlest part of this lesson, if there is one. It's not that big of a deal, though. So we need to create another thing in here. So we're going to call it p hat sub pooled. And you do that by going 45. So bear with me, I got to make this equation editor thing work. Plus 42 over 234 plus 251. That's pooling all the data together. Does that make sense to you guys? So you get a pooled p hat, which turns out, I'll just tell you, is 0.179. And that is what you're going to use down here to create a more accurate standard deviation for this hypothesis test. So we're going to put 0.179 times what's 1 minus 0.179. I think that is 0.821. We're going to do that over one of the sample sizes. And then we're going to add the same estimate over here. This is a more accurate way to do it, and it really tests as to whether you understand the nature of standard deviation estimators. So if you had done the other thing on the AP exam, if I remember correctly when we looked at their sample problems, it's not like you lost a whole ton of points if you did it the other way, but you'd lose a point. And if it's out of 4, that might be a big deal, you know. Okay, so that's the way you do it. Now, I want you to look at your card that I gave you, your yellow card. Is this the way it shows it on your yellow card? It is not. Do they have two different things, though, in that spot for the difference of sample proportions? They do. What's theirs? Theirs is... Oh, I need to make this smaller. Theirs has this square root, and it goes p times 1 minus p. Well, what's p and p? There's no 1p here. What must they mean? They must mean the pooled one. Because if we're assuming that these are equal up here, once again, if I have a blue mark here, then there's only one. It's the pooled one. That's why they only write it as one thing. That should make sense. Okay? So that will be our 0.179. And 1 minus p would be our 0.821. You can do this either way. I'm just showing you the idea between it. And then they have what? They have the square root of 1 over n1 plus 1 over n2. So I put an equal statement in here. You got to put your other stuff on top, right? Your point. What was the guys? 192 minus 0.167. We don't need to put the 0 on there, but I'll put it just to be consistent. Are those statements algebraically equal? I claim they are. My kids who have calculus, or pretty much everybody in here, should be at the level where they can see that these are equivalent statements. How do you get from here to there? What does this share? That is factored out inside the square root, and then you'll have the square root of that stuff that I factored out. You guys got me? Don't make me write all the stuff. I can't handle it. My mouse just can't handle it today, okay? And then what do we have left? What's left when we factor it out of this one? 1 over this. And what's left when we pull it out of the other one? 1 over that. And then square roots have this magical property which you've used forever to like simplify things. Like you guys know how to do the square root of 24, don't you? Don't you go, that's the square root of 4 times, oh, square root of 24 is a bad choice. No, that's fine, it's fine. 4 times 6. And then can't you go that that's 2, not that 2. 2 square root of 6. Use that same thing on this and you get that. Beautiful. A little bit of mathematics today. I love it because we've been focusing on
Teachers,
logic.
will you please release the boys and girls JV basketball team?
Okay, so the last thing we want to do today is create a 95% confidence interval. Let's just skip that part. We could, of course, do it. It's just another one of those same kind of problems. Let's just write our conclusion and call it good. Oh, we need a number. So I'm going to tell you the number? So, after you do all this stuff, that's the z, right? So the z is going to be, yes, I do totally need to tell you that. So supposedly the answer key tells me that the z is going to be, after doing all this stuff, 0.716. Is that our p-value? No. Can anybody tell me, without even looking at the book, is this going to be a large or a small p-value? It's going to be large because it's 0.71 standard deviations. That's not very far away, right? But here's the thing. Here's 0 on the z curve. Here's 0.716. We're, of course, looking above. So we're interested in this area for our p-value. I think it's going to be large. In fact, the p-value for this guy, when I looked it up in my table, well, I didn't look this up. The answer key looked it up. So the answer key says that it's 0.24 about, which makes sense to me because it should be pretty large. So that's not very far away, 0.7 standard deviations. So now we can finally make a conclusion. Should we reject or fail to reject, ladies and gentlemen? That is a large probability, 24% chance of seeing what we saw or something even more extreme. So we failed to reject H sub O. There is, help me phrase it, I'm going to be looking for this exact wording. Only other thing I'm going to take is not enough. Or I guess if you're creative and say it the right way, another way, but it's not going to happen. There is insufficient evidence to suggest that the difference in, how do we do it? Do we go men versus women or women versus men? We went men versus women. Doesn't matter. Difference in men's literacy rates versus women's literacy rates is There's insufficient evidence to suggest that there. It won't let me type all of a sudden. What the heck? I think my computer's giving up on life. I fixed it up like that. Does that make sense? There's insufficient evidence to suggest that there's actually a difference, right? We can't detect it. It's not unusual enough. 24% chance of seeing what we saw. That's not unusual. I think that's it. I think that's what we can say. But we should probably narrow it down. So the exam will probably mark you off a little wee bit if you didn't reference your population of interest. What's my population of interest? If you want to be careful, if you aren't sure exactly what your population of interest is, then say yes, exactly. Come on, it's only one more phrase. You can do it. Yes. This is Statistics signing off.